second part of your unit 1, basic electrical properties of MOSFET, for which you require NMOS. So because we are studying MOSFET characteristics, we require NMOS, how it looks.
Sir, record.
So your NMOS transistor cross-sectional consists of two N plus regions in a P substrate. The substrate is also called bulk or body. It is a lightly doped material. So in some textbooks, it is referred as P minus or P sub P. And the carriers are, because it is NMOS, the carriers are electrons. They're formed in the channel region. The channel region is nothing but the distance between source and drain, or the region below the polysilicon or SiO2 layer. Okay. So which is represented here as small l, representing channel length. Two source and drain regions are formed, as you have seen in two earlier classes. How fabrication is done to get N-channel MOSFET into the layers of silicon. So two N plus regions are acting as source and drain. Your oxide is SiO2, polysilicon is metal. So metal, oxide, semiconductor, field effect transistor. So your FET is a voltage control device. So by applying some potential difference between gate to source, your channel is formed. So how channel is formed? P type is having minority carriers as electrons. Once you apply a gate voltage positive, these electrons are dragged towards the channel. Okay. So and they come and settle in the region below your SiO2 layer. So in here it is not shown, but whenever N and P type are sandwiched, there is a depletion region represented. So source is N plus, drain is N plus, which are formed in a P type. So you can see one depletion region available between NP and PN. So it is like two back-to-back connected diodes. So now the point here is your gate is having some length L. Okay, that is the distance of channel length, and width as W. So these are the dimensions of your transistor. L and W represent the length and width of your polysilicon. L is also your channel length. Okay, so now we want to study the basic electrical properties of MOSFET. So this electrical properties of MOSFET are studied by applying some supply voltage to your terminals. There are 4 terminals: gate, source, drain, and substrate. Okay, so as I'm telling, when you apply gate some positive voltage, electrons will come and settle here. So the minimum voltage required to make channel inversion is called threshold voltage. Okay, so the minimum voltage required to do channel inversion is called threshold voltage. So at which the channel is filled with all electrons. Because it is filled with electrons, we can also represent one depletion region between this channel and P type. Okay, so as I know, you remember NMOS means two N plus regions in P substrate. Metal oxide semiconductor means gate, oxide, and semiconductor, which has dimensions length L and polysilicon width W. And thickness of this oxide is represented as, in some books small d, in some books capital D. Okay. So as you know, whenever I apply some gate voltage, these electrons will come and settle here. The minimum voltage is called threshold voltage, above which the concentration of electrons in the channel will increase. So that is with respect to VGS. As you increase VGS, corresponding electrons in the channel region will increase. Now, at this point, we are telling that source and drain are at same potential. If you apply a potential difference between drain and source, okay, so let VDD is given some positive voltage. What happens when VD is positive? These electrons from source will move to channel. the electrons in the channel will move to drain. Okay, so free electrons will start moving from source to drain. So the carriers always flow from source to drain. These free electrons move from source to drain. Conventional current is nothing but a hole current. In previous diagram, as electron is moving to channel, so one hole is formed here. One electron from channel, if it is moving to drain, one more hole is formed. So electron current is from source to drain. Hole current, the conventional current is moving from drain to source. So, but in general, you remember only one parameter. NMOS means N channel MOSFET, two N plus regions in P substrate. Current carriers are electrons. Conventional current will be opposite to your electrons. So this is a diagram showing depletion region formed between N and P layers. So this N and P are like two back-to-back connected diodes. This is a P-type transistor, two P plus regions in N substrate, metal oxide semiconductor, and the channel region is shown as the dotted line. Difference between P and NMOS is the symbolical representation is three terminals, gate, source, and drain. In most symbols, we don't use the substrate terminal, but there is one more terminal called substrate. And what is the difference between NMOS and PMOS is PMOS devices are represented with a bubble at the gate. So if a bubble is at the gate, that represents symbol for PMOS. Without bubble, it is symbol for NMOS. So we have to see the basic operation of MOSFET. So when you are applying a gate voltage, negative voltage, what happens? Positive voltage will drag opposite carriers, electrons. If you apply a negative voltage, gate, the polysilicon is given a VGS negative. The semiconductor material is filled with all holes. So it is like a two parallel plate separated by some dielectric material. So it is like the carriers get accumulated here. That is called accumulation region, and this is called a it is like a capacitor, two plates separated by dielectric material. So this is the diagram showing when you apply a large negative voltage, VGS negative, this negative at the polysilicon will attract positive carriers below your SiO2. It is like two parallel plates separated by a dielectric material. Now, this is the diagram where VGS is applied positive, but it is less than threshold voltage. So if it is less than threshold voltage, few carriers electrons will come and settle here. And the concentration in the channel region is moving from positive to negative. So the hole density reduces and it is changing to electron density. And once electrons are formed, a diffusion region is shown between the channel and the substrate. So now we are applying VGS some positive voltage. So when you apply VGS positive voltage, you can see source and drain are at same potential in the second diagram. Source and drain are at same potential, but VGS is positive. The electrons are coming and settling in this semiconductor region, and this is called channel inversion. The minimum voltage is called threshold voltage. So what is the condition for the channel to exist is the gate to source voltage must be equal or greater than threshold voltage. Now, after applying VDS, what happens that we are going to study? So when you apply VDS, some positive voltage, these electrons will start moving from source to drain. These electrons will start moving from source to drain. Okay. If you see in this diagram, if VGS is less than 0, an electric field is established across the substrate, that is called accumulation mode. If VGS is greater than threshold voltage, that is called inversion, and the region below the gate will be inverted. If you are applying something between 0 to threshold voltage, the region under the gate will be depleted of charge carriers. So this is VGS less than 0 accumulation region, because the gate is having negative charge. The substrate portion is filled with all holes. So it is like two parallel plate separated by dielectric. So when VGS is greater than 0 and less than threshold voltage, negative charged carriers will come and settle in the substrate. Okay. Now if you see in this diagram, when VGS is greater than threshold voltage, electrons will come and settle in the channel region. Source and substrate are at same potential. So in few other classes, we are going to see why we need to apply a source to substrate potential. But at this moment, source and substrate or body or bulk, they are all equal names. So they are at same potential, and we are applying some VDD, small VDD, positive. So when you apply small VDD, the effective voltage between gate to channel is not uniform like in your previous case. When VDS is also ground, when VDS is at same potential, the gate to channel voltage VGCH, the gate to channel voltage is uniform, and the electrons in the channel are same throughout the channel region. Okay, but when I am applying VDS positive, the gate to channel voltage at source end is more and drain end is less. So that's why you can see in this yellow diagram that yellow region is showing more electrons in towards the source end. They are reducing as you move towards drain end. Okay, because effective voltage is calculated between gate to channel from taking the potential difference between gate to drain also. So gate to drain potential is more here, less here. So based on that concept, we can tell the gate to channel voltage applied at the source end is more. So more electrons are available at the source end, less electrons at the drain end. But even then, as you increase VDS, the carriers in the channel from source to drain will start moving towards drain, will increase. If VDS is less voltage, few electrons will move. If VDS is more electrons will move. Okay, so IDS is directly proportional to VDS. As you increase VDS, current IDS will also increase. IDS represents drain current, drain to source current, which is represented as a whole current. But our conceptual view is electrons are moving from source to drain. In reverse, holes are moving from drain to source. Okay, so try to understand when source and drain are at same potential, channel is formed, no current is flowing. Electrons are formed in the channel, but the electrons will not move. Okay, so that is called a MOSFET cutoff region. MOSFET cutoff region. Once you apply VDS positive voltage, the electrons will linearly increase as you increase VDS. So corresponding IDS. IDS is nothing but whole current moving from drain to source. So as you increase VDS, corresponding IDS increases. This is called linear region or triode region. Okay, in some textbooks it is given as linear region or triode region. So, but if you see here, this will happen up to a voltage of VDS, voltage of VGS minus VTN. Okay, up to a voltage of VGS minus VTN, because above VGS minus VTN, the effective voltage between gate to channel becomes less than threshold voltage. So what happens if you apply a voltage less than threshold voltage? Channel ceases to exist. Channel will not exist. Okay. So the channel will not exist if you apply a voltage below threshold voltage. So, okay. The concentration of carriers reduces. So as you increase drain voltage from 0 to VGS minus VTN, it operates in linear region. Linear region means IDS will linearly increase. But if you are applying any voltage, drain voltage greater than VGS minus VTN, the gate to channel voltage becomes less than VTN. So due to which the channel ceases to exist, such as this diagram. If you see in this diagram, we are applying a drain voltage greater than VD sat. VD sat is nothing but VGS minus VTN. Already gate voltage we applied greater than threshold voltage. Gate voltage is applied greater than threshold voltage. Source and bulk are at same potential. Okay. Gate to channel voltage is more at source end. So more carriers are shown in this diagram. So you can see one linearly increasing curve, but that is stopping at some point of this purple dot. Okay. Because now we have applied drain to source voltage greater than VDS sat, which is VGS minus VTN, due to which gate to channel voltage is reduced to threshold voltage. So channel ceases to exist, and it is that point is called pinch off point. Okay, so the channel at which it ceases to exist is called pinch off point. So till now in linear region, as you increase drain current, corresponding IDS is increasing. That is called linear region, and corresponding current is called drift current. Drift current is the current due to movement of electrons from source to drain, or in reverse it is IDS from drain to source. Okay, but when you operate above saturation region or VD sat, the channel ceases to exist, and the current is a constant current, that is called diffusion current, that is happening due to movement of carriers due to concentration gradient. So this is the linear region representation. The gate to source voltage, when you apply, it is like a voltage dependent resistor, because channel is depending on the gate voltage. So it is like a voltage dependent resistor. So if you see, this is the voltage applied to the gate will turn on the transistor. This green color is the depletion region. We have applied VGS and we have applied VDS. Threshold voltage is VTN. So saturation region, when VGS is greater than VT and VDS is greater than VGS minus VT, you can see pinch off. Corresponding drain voltage is called pinch off voltage. Corresponding drain voltage at which pinch off occurs and current remains constant. Okay, so that is called pinch off. So here we'll see the ID versus VDS characteristics. Y-axis is a current ID in milliamperes. X-axis is VDS, drain to source voltage, and each of the curve is corresponding VGS. You can select first curve VGS or VGS, some specific VGS. Okay, each of the curve is for one specific VGS. What VGS tells? Number of carriers. If VGS is 1 volts, you may have 10 electrons. VGS is 2 volts, you may have 20 electrons. VGS 3 volts, you may have 30 electrons. So the electron density in the channel is decided by VGS, but current conduction is decided by drain to source voltage. That is your x-axis. X-axis 2 volts, less electrons will move. X-axis VDS 4 volts, more electrons will move. Okay, as we increase VDS, more electrons will move. Okay, so in this graph, we have one green color dotted line where corresponding current is increasing linearly with VDS. That is called ohmic region or linear region. But after some voltage of VDS called V pinch off, VDS is greater than VGS minus VTN or VD sat or V pinch off, the current is constant. The current is constant. That is called saturation region. So left side of this green color is called linear region. Right side it is called saturation region. And VGS 0 volts and below that it is no current. Okay. Because current is shown in milliamperes. That is called cutoff region. So this graph is shown for different VGS from 0 volts to positive voltage. And for a MOSFET, the specific threshold voltage is decided by supply voltage. VTN is nothing but 0.2 times of VDD. For a N-channel MOSFET, VTN threshold voltage is 0.2 times of VDD. If you are applying supply voltage 5 volts, your VGS will be 1 volt. So channel inversion occurs at 1 volt. So if you see in the left diagram, here we are calling ohmic region in the right side, and the same terminology here he has written triode region, but he is showing the drain voltages. If you enlarge and see the diagram in your video, in your PPT, the VDS is less than VGS minus VTN because below that voltage of drains to source voltage, the gate to channel voltage will be greater than threshold voltage. But when you are applying VDS greater than VGS minus VTN, that threshold voltage VDS is greater than or equal to VGS minus VTN. This is saturation region. So this is NMOS MOSFET characteristics. So the same thing, the dotted line in our previous diagram, green color, here it is shown with a red points. The transition points below which it acts as a linear region. As you increase VDS, corresponding current will increase. That is shown for a specific VGS. Okay, but what is VD sat? It is VGS minus VTN. So the operation of NMOS is considered for PMOS, where threshold voltage for NMOS is written as VTN. That suffix N represents N-channel MOSFET. Here for P-channel is VTP. Their current carriers are electrons. In PMOS, current carriers are holes. In N-channel MOSFET, VGS is negative positive. In N-channel MOSFET, VGS is positive, VDS is positive, whereas P-channel MOSFET, VGS is negative, VDS is negative. Current carriers are holes here. So the basic operation of N-channel and P-channel is reverse. Voltages, carriers, everything will vary. It is complementary to NMOS. But still PMOS devices are not preferred because the mobility of electrons is 2.5 times more compared to holes. So this is the same thing. The structure of your N-channel MOSFET, consider for PMOS. Consider for PMOS and the characteristics of PMOS, corresponding VDS, IDS. Left to that dotted line represents linear region, right side it is saturation region. You can see VGS is negative, VDS is negative, corresponding IDS is due to holes. So there is one more device, whatever we have discussed till now, it is N-channel enhancement device. P channel enhancement device. What is enhancement device? Channel is formed due to VGS. But there is a device called depletion mode MOSFETs. What is depletion mode is? You can form the channel by implantation method. You can have an inbuilt channel. Inbuilt channel means while fabrication you have made material P type, you have made two N plus regions. Along with that, if you see this pink color diagram, implanted N type channel region. So what is this implanted N type channel region? So if you implant N type channel region, what is VGS required? Already there is an N type. So this is having majority electrons. So no need of gate voltage. So what is the threshold voltage for depletion devices? For NMOS devices, it is 0.2 VDD. For PMOS devices, minus 0.3 VDD. Because threshold voltage for NMOS devices is positive, threshold voltage for PMOS devices is negative, but depletion mode device here, threshold voltage is 0 volts. You don't require any threshold voltage. Gate to voltage, you don't apply anything. Still you apply drain voltage positive. Electrons will move from source to channel, channel to drain, because the channel region is already having N-type region formed by manufacturing itself. Those are depletion devices. So this is one again characteristics for NMOS. But here if you see the middle diagram, VGS is 0. VGS is 0. VGS is negative. Still we can show linear region, saturation region and current conduction because the channel is already having electrons in it. So the gate to voltage of 0 volts will also useful for current conduction. So this is diagram in terms of its layout representations, pattern encodings. So here you can see PMOS are 2.5 times slower than NMOS due to electron hole mobilities. These are the fabrication steps which we have studied in day before yesterday class, that morning class 10 to 11:30. And yesterday class we have seen all the fabrication process in terms of a video. So these are the 10 steps: oxidation, photolithography, diffusion, ion implantation, metallization will give the fabrication of an IC. Okay, so now we'll go for electrical properties of MOSFET. So the first part of your basic electrical MOSFET is the ID versus VDS relation. So we want to derive one relation for ID versus VDS. So the topic is ID versus VDS. So this is your NMOS transistor structure. Here we require only dimensions. We have taken the structure like this. The left side dotted regions represent source and drain. You can see one polysilicon, that is your gate. And in between that thick color, black color is your SiO2. So this source and drain distance is channel length. That is also the length of polysilicon. Also the length of your oxide layer. So everything it is, because below gate oxide only we are calling it as a channel. So this entire channel length is nothing but also the length of your polysilicon. The top view, if you see, this polysilicon is available over width of W. So the dimensions of a MOS transistor are width W, length L, thickness capital D for drain. So how we define the current? Current is nothing but number of carriers moving per unit time. So here it is called transit time. The transit time is number of electrons moving from source to drain. But we represent IDS as whole current because as electron is moving from source to drain, corresponding holes are moving from drain to source. So that's why in terminology we cover only conventional current. Conventional current is nothing but whole current. So IDS stands for drain to source current, which is nothing but whole current. But in reverse, if holes are moving from drain to source, electrons are moving in reverse. So for NMOS, electrons are moving from source to drain. For our current, we cover IDS as number of carriers moving per unit time. So normal current definition that we represent here as IDS is equal to QC by tau. Okay, so QC is nothing but charge induced in the channel. How it is induced? By applying VGS. Okay, so charge induced in the channel divided by electron transit time. So first equation, if you remember, IDS is equal to QC divided by QC divided by tau. Okay, so tau is nothing but transit time for traveling of electrons or holes, because if you cover PMOS devices, we get the same derivation. Okay, so that's why it is written as tau SD. Tau SD is nothing but how time is decided by distance by velocity. How much distance electrons has to traverse throughout channel length. The electron has to move to a distance of channel length. With what? With velocity of v. So time is equal to length by velocity, where L is length of the channel, v is velocity of electrons or holes. So the second equation you have to remember is tau SD is equal to L by V. First equation is I equal to Q by tau. Tau or T, whatever you here in textbook reference, it is tau. Okay. Now velocity of electrons is, we have this equation from your basic EDC. Velocity of electrons is nothing but mobility into electric field. Okay. So these electrons has to move from source to drain. Okay. But you are applying VDS. Okay. You are applying VDS between drain to source. So there is an electric field existing from drain to source. So velocity of electrons is nothing but V equal to mu into EDS. Mu can be electron or hole. So this is written in general for both NMOS and PMOS devices. So mu can be anything. If it is electron mobility, you write mu n. If it is hole mobility, you write mu p. And EDS is electric field between drain to source. If VDS is voltage between drain to source, so there is again a relation. Velocity is equal to mobility into electric field, EDS. But what is EDS? EDS is nothing but VDS by L. There is a potential difference applied between drain to source, due to which there is an electric field between drain to source. So this electric field between drain to source, EDS, is nothing but VDS divided by how much distance? It is length L. So now you substitute this EDS. EDS is VDS by L. Substitute in the previous equation 2.3. We are already having velocity is equal to mobility into EDS. What is EDS? EDS is VDS by L. By substituting there, you get V is equal to mu into VDS by L. But already we have considered what is tau. Tau is nothing but L by V. If you remember, tau is equal to L by V. So there is a L. V is already we got here. What is V? Mu into VDS by L. So L goes to the numerator and becomes L into L, L square. So the final definition for transit time is tau SD is equal to L square by mu into VDS. So this is just a mathematical equation done to get current at each point of your drain voltage. So tau SD is equal to L by V. Already we are having V is equal to mu into VDS by L. You substitute mu into VDS in the denominator. L goes to the numerator. It becomes L square by mu into VDS. So you finally remember this equation. We got one final equation for tau SD. And if you see here, if you are applying VDS, what happens? VDS is more positive. Electrons are dragged towards drain. Okay. So as you increase VDS, corresponding time taken by electron to move from source to drain reduces. Okay. See here, L is time is proportional to L, inversely proportional to VDS. Under the effect of VDS, electrons will move slowly. Corresponding time will be more. So VDS is, if you increase more VDS, corresponding time required for electrons to traverse reduces. But if you increase channel length is small, corresponding time is small. If channel length is more, these electrons have to move a large distance. Okay, so corresponding time increases. So it is more easier to remember. Time taken by electron to move from source to drain is directly proportional to L, indirectly proportional to VDS. The electron and hole mobilities are given at room temperatures. One is 650 centimeters square per volt second. Another is 240. So it is almost 2.5 times. Electron mobility is more. Now we'll see the linear region, the non-saturated region. So here the effective gate voltage is called VGCH, but it is written as VG here. The minimum voltage required to establish the channel is threshold voltage. The minimum voltage required to establish the channel is threshold voltage. So above threshold voltage, whatever you apply, that will increase the concentration of electrons in the channel. If VGS is positive, 1 volt, you get 5 electrons. You just analyze. VGS is nothing but gate to source voltage. If it is 1 volt, if it is 5 volts, for example, I'm telling, if you are taking some VGS of 5 volts, you get some 10 electrons. If VGS is 10 volts, you get 20 electrons. So corresponding VGS will increase carriers in the channel, but that will be above threshold voltage because the minimum voltage required to establish the channel is VTH. So whatever you apply more than threshold voltage, that will increase the channel concentration. So that's why your VG is nothing but VGS minus VT. Now we are trying to define one equation for QC, charge per unit area, because we want charge induced in the channel, QC. QC is charge induced in the channel. In order to get that, we are covering charge per unit area. Charge per unit area, we have a mathematical equation, epsilon into Eg. If you see 2.8, equation 2.8, the charge per unit area is epsilon into Eg. Epsilon is written as epsilon insulator into epsilon naught. What is epsilon insulator? It is permittivity of SiO2 layer, whereas epsilon naught is permittivity of free space. Okay, so then charge per unit area we are covering. If you want total charge induced in the channel, you have to multiply with area. What is area? L into W, width of the channel, length of the channel. Okay, so QC, charge induced in the channel, is equal to Eg into epsilon insulator, epsilon naught into WL. Now we want to cover, see, already we have covered EDS. EDS, because we are applying a VDS, we are having EDS, but we are also applying VGS. When you apply VGS, there is an electric field between gate to channel. EG stands for, which is nothing but, what is electric field? E equal to V by distance. What is V here? Gate to source voltage. So gate to source voltage by distance. What is the distance between gate and semiconductor? The distance between source and drain is channel length. The distance between gate to channel is thickness capital D. So in general, electric field is nothing but potential difference divided by capital D. Okay, capital D here means thickness of oxide layer. But what is the effective voltage? We have to consider gate to source voltage, which is effective. What is the effective voltage? Minus VTN. So VGS minus VTN. But still we are subtracting one more effect. What is the effect? The average electric field coming in between gate to channel due to VDS. So that is minus VDS by 2. Because there is an electric field between gate to channel, there is an electric field between drain to source because of VDS. So EGS is nothing but VGS minus VT covering, this is effective voltage between gate to channel by thickness capital D. But you have to subtract the electric field due to VDS. So that is represented as minus VDS by 2. So that is the average potential difference applied between drain to source. VDS is voltage difference between gate to channel, assuming substrate connected to the channel. So the IR drop in the channel is same throughout the channel and it is taken average as VDS by 2. So the IR drop in the channel is considered as VDS by 2. So effective voltage between gate, effective electric field, EG, average electric field. It is called average electric field between gate to channel is nothing but VGS minus VT minus VDS by 2 divided by oxide thickness. Now you have to substitute this EG in the previous equation. What is EG? So what is QC? QC is EG epsilon insulator epsilon naught WL. Just substitute this EG in the above equation QC. So you are going to get one more equation. Constant parameters are taken to the one side. Epsilon insulator epsilon naught WL by capital D into this remaining term. Okay. Now you are having QC. Now you are having also tau SD. So what is current? Current is IDS is nothing but QC by tau SD. IDS is nothing but QC by tau SD. So substituting those parameters, QC by tau SD, we get one equation like this. Okay. What is if you see equation 2.8, I think 2.6, 2.6. Tau SD is L square by mu into VDS. IDS is QC. So below which you substitute L square, the denominator mu into VDS goes to the numerator. So mu comes here, VDS goes here, L and L square gets cancelled. So you'll be left with one L in the denominator and remaining constant epsilon insulator epsilon naught mu by D are taken as 1 point into W by L into VGS minus VTN minus VDS by 2 into VDS. So if you substitute QC and tau SD parameters, you get one equation like this. The K transconductance constant is taken as epsilon insulator epsilon naught mu by D. So the first parameter K is epsilon insulator epsilon naught mu by D into W by L into remaining term. Now if you see here, current is directly proportional to width. What is width? Width is nothing but the width of polysilicon. If you are having less polysilicon, width of polysilicon is less. Concentration of carriers in the channel is less. So corresponding IDS is less. Now if you are having small channel length, the current will IDS is more because the electrons has to travel a small distance. So corresponding current will be more current. So IDS is inversely proportional to L, directly proportional to width, directly proportional to gate voltage or effective voltage of gate voltage, which is nothing but VGS minus VTN. And also current is directly proportional to VDS. So we are telling that in linear region, as we increase VDS, corresponding current increases. So as we increase VDS, corresponding current increases. So IDS is directly proportional to VGS minus VTN. IDS is directly proportional to VDS. IDS is directly proportional to width. It is inversely proportional to length. More channel length, corresponding current is less. So as a designer, you have to see that depending on the switching speed, you have to prefer short channel length devices. And this length and width are also decided by corresponding supply voltages. So here the factor K, epsilon insulator, epsilon naught mu by D as taken as K, and W by L are the geometry of the device. Together K into W by L becomes beta. So beta is one more constant. Beta is equal to K into W by L. So I'm substituting beta here. So IDS is equal to beta into remaining parameters. VDS minus VGS, VGS minus VTN into VDS. So in the previous line, we have written VDS. That VDS is taken into the brackets. If you see here VDS in 2.12 equation is taken inside. So already we got VGS minus VTN into VDS minus VDS square by 2. Okay. So this is one final equation for current in 3 regions. Now you suppose you are applying cutoff region. What is the condition for cutoff region? Cutoff region means your gate voltage must be less than threshold voltage. Okay, or equal to threshold voltage. So your VGS is equal to threshold voltage. So channel is formed. But drain to source voltage is given ground. So if channel is formed, electrons are available, but no carriers will move because there is no supply between VDS. Okay, so corresponding current is 0. So that you can calculate by substituting in equation 2.14 VDS 0. If you substitute VDS 0, what happens? Total current is 0. Okay, carriers are available in the channel, but no current, no electron moving from source to drain. Now you apply VDS. Now you apply some VDS linearly increasing from 0 to VGS minus VTN because the saturation point, pinch off point voltage of VDS is nothing but VGS minus VTN. So as you increase VDS, corresponding IDS will increase. So that is linear region, triode region or ohmic region. Okay. Then if VDS is greater than VGSat, so that occurs at a voltage of VDS is equal to VDSat. Your IDS is directly, that is a constant parameter. IDS becomes constant. So equation 2.14 is covered to tell the current versus voltage relation in 3 regions of MOSFET operation. So I hope you are understanding NMOS operates in 3 regions: cutoff, linear, saturation. Now we can get one more equation in terms of capacitance. The geometry, the capacitance formed by gate, the gate to channel capacitance is given by, so the gate to capacitance, you have a basic formula, epsilon A by D. For a capacitance, it is epsilon A by D. Here it is not epsilon, it is epsilon insulator into epsilon naught because you have to consider permittivity of SiO2. So gate to channel capacitance CGCH is equal to epsilon insulator epsilon naught. A is area of this parallel plate. So that is nothing but W and L, and the oxide thickness capital D. Now we want to get equation of current in terms of capacitance. So we are covering one more point. Already we are having K equal to epsilon insulator epsilon naught mu by D. If you combine them, you get one equation K in terms of CGH. Okay. You get one equation in terms of CGH. So substitute this K value in the equation where we are having an equation for K. Okay. So K in terms of CGH. You substitute that value in here. Okay. So you get one more equation showing the current in terms of gate capacitance. So IDS is equal to mu into CGH divided by L square into remaining point. So IDS is equal to mu into CGH by L square. And the remaining point is same. Remaining is it is directly proportional to voltages. Here also, if you see, the current is inversely proportional to length. As you increase length, corresponding current reduces. Now we consider one more point, gate capacitance per unit area, that is called oxide capacitance. Gate capacitance per unit area, COX, is nothing but CGH by area. So again you substitute in place of CGH, CO. So you'll get one more equation for current as IDS is equal to mu into W by L into C naught into this. So this all three formulas you get in one big you get one question for derivation of ID versus VDS, or you may get a question in terms of calculating the drain current by providing these constants. So he may give one of the constant, you have to calculate another constant, then substitute in this and find out drain current. So that was linear region or non-saturated region. This is saturated region. So in saturation region, when it occurs, when your drain voltage becomes pinch off voltage. When it becomes pinch off, when you are operating equal to or above VGS minus VTN. So if your drain voltage is becoming equal to or greater than VGS minus VTN, the effective gate voltage reduces to threshold voltage. So this is occurring at saturation point. So we substitute in our previous equation. Any equation you consider, substitute VDS is equal to VGS minus VTN. When you substitute VDS is equal to VGS minus VTN, you get these three equations where one equation 2.17 is in terms of K into W by L, 2.18 is in terms of beta, 2.19 is in terms of CGH, gate to channel voltage. Then 2.20 is in terms of gate oxide capacitance per unit area. So these are the four equations. You may get problems on this topic. So this covers your first part, ID versus VDS relation. We will see VGS less than VT, cutoff region, no current. VDS less than VDSAT. What is VDSAT? This voltage. VGS minus VT. VDS is equal to VGS minus VT. VDS is equal to VGS minus VT. If you are operating below that, means from 0 volts to or some threshold voltage to, we can't tell 0 because this is an enhancement device. So if it is from something from 0 to VDSAT, it is linear region. So IDS is proportional to W, inversely proportional to length, directly proportional to gate to source voltage, directly proportional to drain to source voltage. But if you operate above that, the last equation, it is beta by 2. If you see, every parameter is constant, that is related to manufacturing. WL, they are constant. Mobility constant. K constant. Beta constant. So how that current is decided? That is related to gate to source voltage, effective voltage between gate to source voltage. So it is not depending on VDS. So the current is constant in saturation region. So this is a diagram. First diagram is representing depletion mode device. So that's why your VGS is shown in between. VGS is 0 volts and above. It will operate in three regions: cutoff, resistive, or saturation region. VGS is somewhat negative. Then also we can draw the graph because carriers are available due to inbuilt channel. So same characteristics, NMOS depletion devices. Only thing is gate to source voltage is 0 volts and above. Because threshold voltage VTH is 0 volts. Below that also, in negative voltage also, it will operate because there is an inbuilt channel. And NMOS enhancement device. VGS is 0.2 VDD because the minimum threshold voltage is required is 0.2 VDD. Threshold voltage VGS is equal to VTH, that is 0.2 VDD. And above that if you operate, what happens? The channel concentration increases and correspondingly it operates in resistive saturation, and VGS below 0.2 VDD, it is cut off. So wherever I'm showing the cursor, that is cut off. This is resistive, this is saturation. MOS threshold voltage. So the threshold voltage VT is given by some mathematical equation. So because it is all related to your charge carrier, charge concentration, threshold voltage VT is given by phi into ms into QB minus QSS divided by C naught plus 2 phi Fn. So this is one formula. Based on that, one more equation is generated. These equations are required because you may get problems on this topic. QB, what is QB? QB is charge per unit area in the depletion layer beneath the oxide. So in our previous derivation, we have written it as QC because it is channel. At that time, it is shown as QC. Okay. In this topic, it is the same charge, but it is charge per unit area in the depletion layer. So whatever the channel we are telling, that's why we told it as QC. Here also it is same, but we are writing QB suffix B because it is beneath the oxide. Okay. Beneath the oxide is nothing but that channel region. QB is charge per unit area in the depletion layer beneath the oxide. QSS is the charge density at Si to SiO2 interface. C0 is capacitance per unit area. Phi ms is nothing but work function difference between gate and Si. Phi Fn is nothing but Fermi level potential between inverted surface and bulk Si. So this is one mathematical equation for finding threshold voltage. So if you see equation 2.22 is an expression for QB. So QB is equal to square root of 2 epsilon Si Q into capital N and the remaining parameters. What is phi Fn? It is Fermi potential between gate. Phi Fn is Fermi level potential between inverted surface and Si. So it is a Fermi level potential between the channel area and the substrate. So that is written here as 2.22, 2.23, and the crystal concentration, depending on the crystal concentration, QSS, charge density between silicon to SiO2 interface will vary from 1.5 to 8 into 10 power of minus 8 coulomb per meter square. So in this equation 2.22, we have written something VSB. VSB is nothing but potential difference between source to bulk. So in all the topics we covered that source and substrate are at same potential. Source and substrate are at same potential. So VSB is 0 volts. Okay. But in real, what is required? Your substrate is P-type and your MOSFET is available in an IC and millions of MOSFETs are available adjacent. So the basic operation of MOSFET must not disturb the adjacent MOSFET. So what we have to do? Source and substrate are N and P type. So there is a depletion region. Channel filled with electrons. It is depleted of carriers, holes. So again N and P type. There is a depletion region shown. Drain and substrate. Again N and P type. Okay, depletion region shown. So this depletion region N and P type sandwiched is nothing but two back-to-back connected diodes. Okay, but this basic MOSFET must not affect the characteristics of adjacent MOSFET. So what is the best thing we have to do is we have to see that depletion region is reverse biased. Okay, so how you make it reverse bias? Okay. you have to apply some potential difference between source to substrate. Source to substrate, you have to apply some potential difference. So VSB is substrate bias voltage, a negative with respect to source for NMOS, positive for PMOS. Okay. And Q is 1.6 into 10 power of minus 19 coulombs. N is impurity concentrations, acceptor or donor. So this is written both for NMOS and PMOS. Epsilon SI is relative permittivity. Ni is intrinsic electron concentration. K is Boltzmann constant. So after substituting all those parameters, we have one equation, the change in threshold voltage as you apply VSB, because now you apply VSB, when you are applying VGS, electrons will move towards the channel, but these electrons will have a similar effect because these electrons are applied also some potential difference from source to bulk. So that's why threshold voltage is not only VT, it is somewhat more when you apply substrate to source voltage or substrate bias voltage. So when you apply VSB, your threshold voltage is not only VT, it is an equation given by something, the final one. Okay, this is the final one. This is got by doing some analysis here. Delta VT is proportional to gamma into VSB whole power of 1 by 2, means square of VSB. Gamma is a constant depending on substrate doping, and this is more lightly doped substrate. So if you are doping more, substrate is doped more, the body effect will be less. So corresponding VT is given by VT naught plus gamma into square root of this all parameters. Now suppose if VSB is 0, VSB is 0, VSB is negative for NMOS, positive for PMOS. If VSB is 0, what happens? VSB is 0 means the square root of terms, they get automatically cancelled and you are left with only threshold voltage. So threshold voltage VT naught of 0 represents threshold voltage for VSB is equal to 0. If you don't apply source to bulk voltage, the threshold voltage is VT naught. If you are applying one potential difference between source and bulk, your threshold voltage will be slightly more, which is given by this final equation. So this is body effect. Along with that, threshold voltage is increasing by a parameter of gamma into the square of these terms. So you have a chance that you get a problem or you get a small question for 2 marks. What is threshold voltage? What is body effect? And gamma is body effect constant or body parameter, which is given by square root of 2q epsilon SI 2q epsilon SI into capital N divided by COX. What is Q? Charge epsilon SI, SiO2 permittivity, capital N acceptor or donor concentration, COX oxide capacitance. So this is the expression for threshold voltage. And here he want to represent along with threshold voltage. If VSB is 0, what is threshold voltage? 0.2 VDD. If VSB is 5 volts, threshold voltage is 0.3 VDD. For NMOS enhancement devices. Similarly, NMOS depletion devices. Okay, so this is based on some analysis. So that is your threshold voltage and body effect. We have a concept called transconductance. What is transconductance? What is conductance? Conductance means the property, the ability to conduct. So it is reverse of resistance. So you analyze conductance is reverse of resistance. Means conductance is represented by G. Resistance is represented with small r. So conductance G is inversely proportional to R. Conductance G is equal to 1 by R. Because it is conductance, that is resistance. Conductance and resistance are having reverse property. Resistance is nothing but opposition for electrons. Conductance means ability to conduct. So G is equal to 1 by R, and what is resistance? Resistance is equal to voltage by current, V by I, R equal to V by I. So then G is equal to I by V, because G is equal to 1 by R, G is equal to I by V. G is equal to I by V. But here we are calling it as transconductance. What is transconductance? Here, what is the final parameter? Current. What is the input parameter? Gate voltage. You are applying gate voltage, VGS. Electrons come and settle in the channel. And drain voltage will make corresponding current move. Okay. So transconductance is nothing but output current by input voltage. What is output current? Rate of change of IDS with respect to rate of change of input voltage. You apply gate voltage only 5 volts, 10 electrons. Okay. You apply 10 volts, 20 electrons. Means gate voltage will increase corresponding current. Okay. So transconductance means it is related to conductivity. So as you increase VGS, corresponding the rate of change of current with respect to VGS is transconductance at constant VDS. So this is calculated at constant VDS. So already you are having the definition for current IDS as QC by tau. Here I require tau. So I'm taking tau as nothing but QC by IDS. Now, from which you can consider rate of change of IDS. Rate of change of IDS is nothing but dou QC by tau SD in equation 2.26. If you see in equation 2.26, dou IDS is nothing but dou QC by tau SD. Dou IDS is nothing but, you consider only IDS. IDS is QC by tau SD. Rate of change of current, because time is constant. As you increase gate voltage, more carriers will come and settle in the channel. More current will increase, but the time taken will be same because the drain current VDS is constant. So rate of change of equal to dou QC by tau SD. But what we have this equation. Now tau SD is constant. Tau SD is a constant depending on VDS. VDS is constant now. Length is constant. You have already manufactured MOSFET. So length is constant, mobility is constant, VDS is constant. So tau SD is constant. Now dou IDS is equal to dou QC by tau SD. Already we are having dou IDS is equal to dou QC by, substitute your tau. It becomes mu into VDS by L square. So you have a basic equation of charge to voltage Q equal to CV. Dou QC is nothing but CG into dou VGS. Okay, so you can just analyze what is dou QC. It is CG, gate to capacitance, gate to channel capacitance into dou VGS. Substitute that value, equation 2.28 in 2.27. After substituting 2.28 in 2.27, you get dou IDS as CG into dou VGS into mu into VDS by L square. Already mu VDS by L square is same. Only we are substituting dou QC. Now what is GM? GM is nothing but rate of change of IDS by rate of change of VGS, which is nothing but just take the parameter rate of change of VGS, dou VGS to the left side. You get transconductance GM, which is nothing but CG constant, mu constant, L constant into VDS. So how transconductance is computed? At constant VDS, it is inversely proportional to length. So if you go for small channel length devices, transconductance is more. So by substituting VDS value in saturation region, VDS is VGS minus VTN. You get this equation. So these all equations are useful for small problems in the part A if it is done in your syllabus, or objective mid-exam bits, or in your gate related exams. So wherever you require MOSFET characteristics, you require all these parameters. GM is proportional to VDS, inversely proportional to L square. So again, we are going to cover a few more equations you can generate. Already we are having gate to channel voltage, gate to channel capacitance. This equation, which are I'm showing that equation, you substitute in CG, you get one more equation. Okay, one more equations where you can get 2.32. 2.32. You can get 2.32. GM is equal to, see, we are just starting with our GM as dou IDS by dou VDS, output current, rate of change of output current with respect to input voltage, taking your current equation, just doing partial differentiation, you get one more analysis that we have substituted here. So dou IDS is nothing but dou QC by this tau. Tau already we have substituted. So just dou QC is calculated. That is again kept in the equation. So finally we got GM in as 2.32. 2.32. GM is 2.32. Again, if you consider first parameter is K into W by L is beta. So in terms of beta, it is GM is equal to beta into the remaining terms. So the resistance of FET in linear region near the origin is known as on resistance, and resistance is nothing but inverse of transconductance. So for that, the equation is 1 by beta times of this one. And how to increase the transconductance? Transconductance GM can be increased by increasing the width. And if you increase the width, what happens? The area of a capacitance A equal to WL. So as we increase the width, area increases, input capacitance increases. And what is output conductance? The name itself telling it is output conductance means output current by output voltage. What is output current? IDS. What is output voltage? VDS. So dou IDS is nothing but rate of change of IDS by, here it is shown wrong, it is rho IDS by dou VDS. So which you can get as inversely proportional to L. For a MOS device, the strong dependence of channel length is represented as IDS. Actually, he has shown the direct equation with one lambda constant, lambda into IDS, and you get inversely proportional to L. Both conductance and transconductance, output conductance, are inversely proportional to channel length. So if you go for small channel length, conductance is more. Conductance is more means more electrons can move towards drain and corresponding IDS will increase. So the basic electrical properties of MOSFET covers current equation in three regions: cutoff, linear saturation, and corresponding threshold voltage, and how it is varying with respect to body effect, how threshold voltage is increasing, then output conductance, then transconductance. These all parameters are the properties of MOSFET. So when a person becomes circuit designer in VLSI, he can control the parameters of MOSFET such that he can achieve a faster circuit, low power dissipation circuit, small area circuit. See, from designer side, from customer side, it is speed and power consumption. He will not, because area is also one parameter, but if it is faster and low power consumption, one person will compromise for area. But speed is the main constraint now. In the present design technology, speed is the main constraint. Everyone prefers speed, devices which operate faster. So that speed parameter here, it is covered as figure of merit. For a MOSFET, for a person, it is speed. Okay, so figure of merit is covered in terms of its speed parameter. That is nothing but W naught, because we know what is W naught. W naught is a symbol for figure of merit. It is a measure of frequency response. Frequency response means how fast it can switch from cutoff to saturation, saturation to cutoff. Okay, so figure of merit is defined as GM by CG. Already we know what is a GM. Substituting GM in that equation, you get figure of merit as mu into VGS minus VTN divided by L square. W naught is equal to 1 by tau SD. So finally we conclude W naught, figure of merit. For a MOSFET, figure of merit is not inversely proportional to tau SD. So switching speed depends on mobility. You select P-type devices. Their mobility is less. So if you go for NMOS devices, you can get transistor switching speed more because its mobility is more. Then gate to source voltage above threshold voltage. You apply threshold voltage minimum is 0.2 VDD. Instead of operating above 0.2 VDD, you apply more effective VGS, that is effective voltage, VGS minus VTN. If VGS minus VTN is less, corresponding switching speed is less. If VGS minus VTN is more, corresponding switching speed will be more because there are more carriers. Okay, then it is inversely proportional to square of channel length. From equation 2.34, if you see, it is inversely proportional to square of channel length. A high switching speed devices will have high GM. So when you are designing one logic with a different number of transistors, where you require more switching, there you have to select high GM devices. More mobility, mu n you have to select. So this is the threshold voltage due to body effect, change in threshold voltage, delta VTS. The final equation which we have seen, if VSB is 0, gamma the center parent becomes 0. So that is related to threshold voltage. Threshold voltage is increasing by delta VTH, gamma into square of VSB plus the remaining terms. Square root of 2 phi s plus VSB minus square root of 2 phi s. So this is MOS transistors operating in 3 regions: cutoff or subthreshold region, linear or non-saturated region, and saturation region. In cutoff region, VGS is less than VT, so corresponding current is 0. In linear region, we are applying VGS greater than VT. VGS means gate to source voltage, which is greater than VT, whereas drain voltage is less than VD sat. Drain voltage is less than VD sat. So corresponding equation, this we have generated. We have 4 different types of equations. There in terms of beta, this is one equation. This is shown for PMOS. I think this is some page is missing. 2. This noise margin, this all will come when we go for a specific device, basic inverter. This power dissipation we will cover when we go for CMOS inverters. So this is not specific to our topic. So this is something called pass transistor. Pass transistor means already you know your NMOS devices or PMOS devices can act as a switch. So what is a switch model? Switch model means source and drain are 2 terminals of your switch. Gate is your control terminal. For a NMOS devices, VGS, if you apply some positive voltage, okay, then the switch is closed. If you don't apply, VGS is 0, then it is as an open switch. Okay, so that open switch, closed switch, MOS transistor as a switch. But there is a this is NMOS acting as a switch. So you apply now source voltage V in as some 0 volts. In terms of logic levels we are covering here, already VGS is 0 volts means it is an open switch. But VGS, you apply some positive voltage. VGS, if you apply some positive voltage, then it is like a closed switch connecting your source and drain. But because if you that is a switch model, but in real, what is happening is the minimum voltage required to establish the channel is threshold voltage. So if VGS is logic 1, V out is V in. You try to understand this V out here it is A, sorry, V out here it is B, V in is A. When I apply logic 1, switch is closed. What is VB? What is output? Which is nothing but input. But for logic 0, you apply logic 0 at the input, you get output at logic 0. But you apply logic 1, which is nothing but something as VDD. You apply input VDD, you get VDD minus VTN. What is VTN? What is VTN? This is the minimum voltage left over in the needed to establish the channel. So when you apply either end as logic 0, you get output as same. So what is this pass transistor is? NMOS devices are poor in transmission of logic 0. PMOS devices are poor in transmission of logic 1. There is a drop of threshold voltage due to channel requirement. So whenever you apply input logic 0, you get logic 0 at the output. If device is on, if it is a closed switch, but if you apply VDD, you get output as VDD minus VTN. So there is a drop of threshold voltage. So NMOS devices are poor in transmission of NMOS devices are poor in If you apply logic 0, you get logic 0 at the output. If you apply logic 1, you get logic 1 minus VTN. Okay, so NMOS devices are poor in transmission of 1, PMOS devices are poor in transmission of 0. So for that, we are combining both NMOS and PMOS, and we are creating one more device called transmission gate or bidirectional switch. Okay, transmission gate or bidirectional switch, where if you see the below diagram is an NMOS, control pin is S. Okay, one terminal, both source and drain terminals are connected, and because NMOS and PMOS are complementary, the control pin S here becomes S bar. The symbolic representation is this diagram. You can see control is one terminal for gate, control bar is another terminal but represented with a bubble. Bubble represents it is a PMOS device. Without bubble it is NMOS device. Now the drawback of pass transistors is eliminated by a bidirectional switch or transmission gate, where the NMOS devices are poor in transmission of 1, PMOS devices are poor in transmission of 0. That is nullified by, because when you apply logic 0 at A, switch is closed, one of the devices will allow or good in transmission of 0. So output you get logic 0. You apply logic 1. If NMOS devices are poor, PMOS devices are good in transmission of 1. So you get logic 1 received at the output. So by combining both NMOS and PMOS as a bidirectional switch or transmission gate, your logic levels are retained. So this is used in as a switch logic. Okay. So for today, this is covered certain topics of your second part of unit 1. Already you know what is an NMOS, what is the symbol, what are the terminals, what are the characteristics. For next class, we are going to combine your NMOS and your PMOSs. We are going to create basic gates and how they are operating. Okay, so I'll take attendance. Then anyone, if they are having doubts, they can ask me. Okay, already it is almost 1:15. I want to end the session. If you are having any doubts, you can ask me, or I will end the session within 5 minutes.